Hello and welcome to this ACUMEN educational video. In this short lecture, I will showcase the core innovations in multimodal management resulting from this exciting Horizon Europe project. We begin with a simple outline. I will first discuss the goals and objectives of Work Package 4, entitled AI-powered seamless integrated multimodal traffic management. After that, task by task, I will highlight the key findings and insights that contribute to future seamless mobility. The main objectives set forth for Work Package 4 are as follows: to identify and improve traffic performance on worst-case scenarios through structure sampling, what-if simulation analysis, to assess and improve existing state-of-the-art management strategies to achieve multimodal seamless travel, identifying opportunities for mutual improvement across different modes, to abstract management strategies through model-free AI-based approaches, ensuring flexibility and computational efficiency in large-scale networks, and to facilitate orchestration in multi-stakeholder interactions through enhanced digital twin functionalities considering game theoretical aspects. We begin with task 4.1, the stress test scenario generator. Transportation systems often experience disruptions, either at the supply side, for example when considering closures due to roadworks or accidents, or at the demand side, for example when considering extraordinary events. A strong multimodal management system should be designed and equipped to deal with these disruptions. But which disruptions? Transport networks are complex systems, rich with intertwined dynamics. Not every disruption can or should be accounted for. A balance must be struck. This leads to the research question: which disruption is most critical? In order to address the research question, a framework was developed based on three core steps: a disruption sampling step, carried out through Sobol sampling, to rank disruptions by the relative probability of occurrence. The impact of the worst disruptions was then propagated through simulation, and finally, sensitivity analysis was carried out to determine the core factors contributing to said disruptions. Now for some insights. In collaboration with the city of Helsinki, the stress test generator was applied to the city's port area, one of the 4 pilot sites of the ACUMEN project, resulting in maps such as the one on your screen right now. This color coding allows stakeholders to quickly assess which portions of the road network are most sensitive to, for instance in this scenario, road closures. Although similar analyses can be carried out also considering origin-destination zones and signalized intersections. Now, moving on to the second task, towards seamless traffic management strategies. The main objective in this task was to survey existing traffic management strategies and propose improvements that involve multimodal interactions, rather than siloed operations. The overall goal was to improve seamlessness, seen either from the perspective of the traffic operators or from the user's viewpoint. Leading to our core research question: how can seamlessness be further enhanced through traffic control? We approached this problem from multiple perspectives. Considering traffic lights, we looked into how their operations could be improved from a multimodal perspective and the role of vehicle connectivity in achieving this. We conclude that real-time information on travel times and passenger occupancy, both from private and public transport vehicles, can be employed to reduce person delay by as far as 14%. This reduction was furthermore found to be robust even in low penetration rates. Privacy preservation slightly reduces, however, the maximum performance gain that could be achieved. We further considered incentivization strategies, rebalancing in ride-hailing systems, pricing strategies, and dynamic perimeter control. Considering incentives, we observed a reduction of 19.1% in total travel time, even with a relatively small budget, namely about 10% of the total travel time in the network. What we could conclude here is that incentives are effective in facilitating sustainable modal shift, although a break-even point exists, beyond which further incentivization brings quickly diminishing returns. Considering rebalancing in ride-hailing systems, we found instead that waiting time for multimodal trips could be improved by as far as 28.7%, with multimodal travel time variability reduced by 24.8%, and the average total travel time in the network reduced by a staggering 57.6%. Now, what this shows is that, given an appropriate rebalancing logic, ride-hailing services can provide substantial relief in incidental conditions. Considering pricing as opposed to incentives, we compare different approaches. We consider pricing by road versus pricing by trip, and looked into how different pricing regimes, whether you would price only private vehicles or any trip on any combination of vehicles, would impact different key performance indicators. What we could conclude here is that trip pricing outperforms road pricing across all KPIs, with multimodal trip pricing performing best across all tests. Revenue neutrality was also investigated, resulting in an acceptable trade-off between improved equality and fairness and traffic performance. Finally, considering dynamic perimeter control, we found up to a 5% gain in global mean speed with respect to static perimeter control and up to a 3% reduction in total travel time. These gains were further found to be highly dependent on the frequency of update of the perimeter boundary. For the Lyon scenario, depicted here, we found that a 30-minute update window was best suited. Individual management strategies could indeed be extended towards seamlessness. A key disadvantage is, however, that many of these approaches are computationally very demanding. This is where task 4.3 finds its core contribution. In this task, the objective was to develop a framework that allowed to abstract management algorithms so that their execution can be distributed and sped up, thanks to recent advancements in the field of artificial intelligence. To this end, 3 levels of traffic control were abstracted: at the intersection level, at corridor level, and at network level. Starting with the intersection level, we employed reinforcement learning to help assess which intersection should be equipped with the aforementioned connectivity-enhanced signal controllers. We found that identifying the appropriate intersections for deployment leads to improved performance compared to network-wide deployment. At the corridor level, we investigated the potential for dynamically activated dedicated bus lanes, compared to all-purpose lanes and static bus lanes. The proposed abstracted reinforcement learning-based controller was able to strike a better balance between private and public transport performance. At the network level, a deep reinforcement learning-based abstraction of perimeter control was developed, featuring a multi-level hierarchical approach. We found that by balancing queues outside of the protected area with explicit awareness and prioritization of public transport led to consistent reduction of time loss across all scenarios. Finally, the ride-hailing results of task 4.2 were further enhanced through AI-based abstraction, leading to substantial improvements in seamlessness for passengers at network scale. Lastly, task 4.4 considers how to align, select, and deploy the appropriate management strategy at the appropriate time for the appropriate reason. To achieve this, we interact with the ACUMEN digital twin environment and the modules therein to evaluate how different approaches perform and compare. The orchestrator serves as an interface supporting a multimodal manager. A natural language interface allows users to question the collection of models, data, and knowledge docs to, for example, help deciding, for a given situation, who should be aligned and involved among multiple stakeholders. The orchestrator is based on a simple agentic design, with a large language model supporting natural language input and output, and individual agents tasked with, for example, querying documents or simulation and prediction models, say to check for normative compliance or to know what is going to happen in what-if scenarios. This helps to decide which management approach to apply next. A key game theoretical issue, however, arises here. Not all stakeholders will be revealing their objectives, particularly those operating in competitive markets. We therefore investigated whether AI could be employed to reconstruct a stakeholder's goals, captured by a hypothetical or latent objective function. We assume here that we can only operate on directly measurable features collected from the road network, such as detector measurements and revealed management actions. Our results show that inverse reinforcement learning can reach upwards of 97% accuracy on both individual intersection and motorway management strategies. Furthermore, we could conclude that the resulting feature weight allocation correctly reveals the original strategy of the stakeholder in all simulated scenarios. These are very promising results, although more validation is warranted considering realistic aspects such as data noise, disturbances, etc. This concludes this Acumen educational video. I would like to thank you for your attention.